What actually is dark matter? What makes up most of the universe? Scientists say it's invisible, and even after decades of research, they still do not know exactly what it is. This unknown substance is called dark matter, and its presence is inferred from the way gravity behaves on cosmic scales. Galaxies that shouldn't exist. Dark matter does not emit light, absorb light, or reflect light, so it cannot be seen with telescopes, yet its gravitational influence appears everywhere in the universe, shaping galaxies and controlling how they move. The Milky Way rotates steadily, with stars orbiting its center at high speeds. When astronomers calculate how fast these stars should move based on the visible matter, the stars, gas and dust, they find a problem. The outer stars are moving faster than expected. According to gravity from visible matter alone, these stars should escape the galaxy and drift into space. Instead, they remain in orbit, held by a gravitational force that we cannot directly observe. This discrepancy is the first evidence that most of the matter in the universe is invisible. Scientists refer to that unseen mass as dark matter, a substance that outweighs ordinary matter and quietly governs the motion of galaxies. Astronomers have measured these rotation speeds for decades. Observations of galaxies consistently show that the visible matter is only a small fraction of the total mass. Estimates suggest that around 85% of matter in the universe is not detectable through light or conventional telescopes. This matter is real, it exerts gravity, and it outweighs all the visible stars, gas, and dust combined. The first serious evidence for this came from Fritz Zwicky in the 1930s. In the 1930s, Fritz Zwicky, a Swiss astronomer working at the California Institute of Technology, studied a cluster of galaxies called the Coma Cluster. The Coma Cluster is a large grouping of hundreds of galaxies located about 320 million light-years away in the constellation Coma Berenices. Zwicky was interested in understanding the dynamics of the cluster, particularly the velocities of the galaxies within it. By measuring these velocities, he could estimate the mass of the cluster, including both visible and unseen components. Zwicky used the Doppler effect to measure galaxy velocities. When an object moves toward an observer, its light shifts to shorter wavelengths. When it moves away, the light shifts to longer wavelengths. By analyzing the spectra of the galaxies, Zwicky could determine how fast each galaxy was moving relative to the cluster's center. This process allowed him to calculate the total kinetic energy of the cluster, which is directly related to the gravitational forces keeping the system bound. To convert these measurements into an estimate of total mass, Zwicky applied the virial theorem. The virial theorem states that for a system in equilibrium, the average kinetic energy of the components is proportional to the average potential energy from gravity. In practical terms, if galaxies move faster than expected, there must be more mass generating the gravitational pull needed to hold them together. If they move slower, less mass is required. The virial theorem provides a method to estimate the total mass of a system from the motions of its constituents. Zwicky found that the Coma cluster contained far more mass than could be accounted for by the visible galaxies alone. By his calculation, the total mass of the cluster was roughly 400 times greater than the mass inferred from the light emitted by stars. This discrepancy indicated the presence of a substantial amount of unseen matter. Zwicky proposed that this invisible component existed throughout the cluster and referred to it as dunkle materie, or dark matter. The velocities of the galaxies provided the evidence. The galaxies were moving fast enough that without additional mass, the cluster would have dispersed long ago. The visible stars and gas were insufficient to produce the gravitational binding required to maintain the cluster's structure. The only way the cluster could remain intact was if most of its mass was invisible, exerting gravitational influence without emitting or reflecting light. At the time, Zwicky's conclusion was largely ignored by the astronomical community. The idea that most of the mass in the universe could be invisible was unprecedented and difficult for contemporaries to accept. Some suggested errors in measurement or unobserved faint stars could explain the discrepancy. Others believed that clusters were not in equilibrium, so the virial theorem did not apply. Zwicky continued to present his results, but the significance of his discovery was not widely recognized. Zwicky's method relied entirely on measurable quantities, the speeds of galaxies, and the application of classical mechanics. By using the virial theorem, he turned motion into a direct estimate of mass. This approach provided a quantitative measure of mass that did not depend on light. The critical insight was that gravitational influence reveals the total amount of matter, regardless of whether it is visible. Observations of galaxy motion offered a way to detect mass that cannot be seen. Subsequent studies of other galaxy clusters confirmed similar discrepancies. The Coma cluster was not unique. In multiple clusters, the observed motions of galaxies indicated the presence of far more mass than could be accounted for by visible stars. This evidence gradually strengthened the case for a dominant form of invisible matter. Although Zwicky's original work was overlooked for decades, it provided the first quantitative evidence that the majority of matter in the universe is not directly observable. The Coma cluster itself remains a standard example in studies of dark matter. Modern observations use both galaxy velocities and gravitational lensing to map the distribution of mass, revealing that the majority of the cluster's mass is concentrated in a dark component. X-ray measurements of hot gas in the cluster also support this conclusion. These independent methods confirm that the visible galaxies represent only a small fraction of the total mass, consistent with Zwicky's original calculations. The virial theorem remains a central tool in astrophysics for estimating the mass of systems ranging from star clusters to galaxy clusters. Its application does not depend on the specific type of matter. By comparing the observed kinetic energy with the gravitational potential energy expected from visible matter, astronomers can determine how much additional mass is required. In the case of the Coma cluster, the discrepancy between observed and visible mass was extreme, indicating that most of the cluster is composed of material that does not interact with light. Zwicky's work established the first clear observational evidence for dark matter. It showed that galaxy clusters are dominated by mass that cannot be detected through traditional optical observations. Although the physical nature of this dark matter was unknown, its gravitational effects were measurable. The cluster's dynamics demonstrated that dark matter was not a minor component, but a major constituent of the universe. Vera Rubin and galaxy rotation curves. In the early 1970s, Vera Rubin, an American astronomer, began a series of observations that would change the way scientists understood galaxies and the universe. Rubin worked at the Carnegie Institution for Science in Washington, D.C., and she focused on studying the motions of stars in galaxies. Her goal was to understand how galaxies rotated and how mass was distributed within them. At the time, astronomers assumed that most of the mass of a galaxy was concentrated near the center, where the stars and visible matter were densest. According to this assumption, the rotation speed of stars should decrease as their distance from the galactic center increased. This expectation followed directly from Newtonian mechanics and is often called the Keplerian decline, named after Johannes Kepler, who first described the motions of planets in the solar system. In simple terms, planets farther from the Sun move more slowly because the gravitational pull from the Sun weakens with distance. The same principle should apply to stars in a galaxy. Stars near the center, where mass is concentrated, should move quickly, and stars on the outskirts, where there is less visible matter, should move more slowly. Rubin and her collaborators began by studying the Andromeda galaxy, the nearest large spiral galaxy to the Milky Way, located about 2.5 million light-years away. Andromeda is relatively close, bright and large in the sky, making it suitable for detailed measurement of star velocities. Rubin used spectrographs to measure the Doppler shift of light from stars and gas at different distances from the galaxy's center. A red shift indicated the star was moving away, a blue shift that it was moving toward Earth. By plotting these velocities as a function of distance from the center, Rubin could create what is now called a rotation curve for the galaxy. The expectation was straightforward. If visible matter accounted for the total mass of Andromeda, the rotation curve would rise quickly near the center, peak at an intermediate radius, and then decline at greater distances, reflecting a decrease in gravitational pull. This is exactly what Kepler's laws and Newtonian gravity would predict. However, the observations showed something very different. Beyond the central regions, the velocities of stars did not drop off. Instead, they remained approximately constant. Stars at the edges of the galaxy orbited just as quickly as those much closer to the center. This was completely unexpected. The visible matter in Andromeda, which includes stars, gas and dust, was not sufficient to produce this flat rotation curve. The flatness of the rotation curve implied that there must be additional mass distributed throughout and beyond the visible disk of the galaxy. This mass could not be detected through light, either emitted or reflected. Rubin concluded that galaxies are surrounded by massive, invisible halos of matter that dominate their total mass. In Andromeda, the visible stars account for only a small fraction of the galaxy's mass. The rest must be in the form of dark matter. Rubin and her team repeated these observations with other spiral galaxies. The same pattern emerged repeatedly. Every galaxy they studied, regardless of size or distance, showed rotation curves that remained flat at large radii. The Keplerian decline predicted by visible matter alone did not occur in any of these galaxies. The implication was clear. Dark matter was not unique to a single galaxy or a special case. It was a universal feature of galaxies. The massive invisible halos that Rubin inferred were a fundamental component of the galactic structure. The data can be visualized by comparing the predicted rotation curve based on visible matter with the observed curve. The predicted curve rises near the center and then declines at large distances, while the observed curve remains flat. The difference between these curves indicates the amount of additional mass needed to account for the observed velocities. This additional mass is distributed in a roughly spherical halo surrounding the visible disk. The discovery had major implications. For one, it confirmed that Zwicky's observations of galaxy clusters in the 1930s were not an isolated phenomenon. While Zwicky had identified missing mass in the Coma cluster, Rubin showed that missing mass also exists within individual galaxies. Dark matter is not just a property of galaxy clusters, it is integral to every galaxy's structure and dynamics. Rubin's work also provided a clear framework for modelling galaxies. By incorporating a dark matter halo, astronomers could accurately reproduce observed rotation curves. The mass of the halo generally exceeds the mass of the visible stars by several times, and its extent reaches far beyond the luminous disk. The dark matter halo explains not only the flat rotation curves, but also the stability of spiral galaxies, which would otherwise be prone to disruption if only visible matter were present. This finding prompted a shift in how astronomers think about galaxies. Before Rubin, galaxies were often modelled primarily based on the distribution of visible stars. After Rubin, any realistic model had to include a dark matter halo to match observations. The halo is now considered a basic component of a galaxy, along with the central bulge, the disk, and the interstellar gas. Rubin's observations also influence cosmology. If most galaxies have dark matter halos, then dark matter must be a major component of the universe as a whole. It cannot be explained by ordinary baryonic matter, such as stars or planets. This conclusion led to the development of modern cosmological models, in which dark matter constitutes about 27% of the universe's energy density, with ordinary matter making up only 5%. Dark matter is necessary to explain not just individual galaxies, but also the formation and evolution of large-scale structures in the universe. The method Rubin used was careful and systematic. She measured velocities of stars and gas at multiple points along a galaxy's disk, corrected for observational effects, and ensured that the measurements were accurate and repeatable. Her results were confirmed by subsequent studies using different instruments and techniques, including radio observations of neutral hydrogen gas, which extended the rotation curves even further into the outskirts of galaxies. In every case, the flat rotation curve persisted, reinforcing the need for a massive dark matter halo. Rubin's work also addressed alternative explanations. Some scientists suggested that the laws of gravity might differ on galactic scales, as in modified Newtonian dynamics, EOND. While MOAND can explain flat rotation curves in some galaxies, it struggles to account for observations in clusters of galaxies, the cosmic microwave background, and gravitational lensing. Dark matter provides a consistent explanation across multiple phenomena, which is why it became the standard interpretation. The dark matter halo model now dominates galaxy studies. Rotation curves of spiral galaxies are routinely used to estimate the mass and distribution of dark matter. The halo is thought to be roughly spherical, with a density that decreases with distance from the centre, but extends far beyond the visible disk. Its exact composition is unknown, though candidates include weakly interacting massive particles, WIMPs, and other hypothetical particles. Rubin's observations were the first clear, direct evidence that these halos exist and dominate the mass of galaxies. Rubin's work also demonstrated the importance of careful measurement and systematic observation. By focusing on individual galaxies rather than clusters, she provided evidence that dark matter is a universal property of galaxies. Her rotation curves became a benchmark for testing galaxy models and for constraining theoretical candidates for dark matter. They also provided motivation for further searches, both direct and indirect, to understand the physical nature of the unseen matter. The implications extend beyond galaxy dynamics. Dark matter affects the formation of galaxies in the early universe, the distribution of galaxies in clusters, and the large-scale cosmic web that structures the universe. Simulations of galaxy formation that include dark matter produce results that closely match observations. Without dark matter, these simulations fail to reproduce the sizes, shapes, and rotation speeds of real galaxies. Rubin's measurements provided the empirical foundation for this theoretical framework. Vera Rubin's observations of galaxy rotation curves in the 1970s established that stars in galaxies move at velocities that cannot be explained by visible matter alone. Flat rotation curves indicate that galaxies are surrounded by massive, invisible halos, containing far more mass than the luminous components. This phenomenon is universal, present in nearly all spiral galaxies, and confirms that dark matter is an essential component of galaxies and the universe. Rubin's work transformed the study of galaxies, provided strong evidence for dark matter, and remains a cornerstone of modern astrophysics. What dark matter is not. The universe contains far more matter than what we can see. Stars, planets, gas, and dust account for a small fraction of the total mass inferred from gravitational effects. The remainder is dark matter, but understanding what dark matter actually is requires first eliminating what it is not. Early in the search for the unseen mass, astronomers considered ordinary but faint objects that could escape detection, and these possibilities needed rigorous testing. One of the first candidates was a category collectively known as MACOs, or massive compact halo objects. These include brown dwarfs, black holes, and other objects that are massive but emit little or no light. Brown dwarfs are objects with insufficient mass to sustain hydrogen fusion in their cores, making them dim compared to stars. They can be as small as a few percent of the Sun's mass. Rogue planets, planets not bound to any star, also fall under this category. Stellar mass black holes, the remnants of massive stars, were considered another option. If galaxies were surrounded by halos of these faint objects, their combined mass could, in principle, account for the gravitational effects attributed to dark matter. Testing this hypothesis required observing the effects of these objects on light from background stars. The method of gravitational microlensing provides a way to detect objects that emit little or no light. When a massive object passes between a distant star and an observer, the gravity of the intervening object bends the light from the background star, temporarily brightening it. This phenomenon allows detection of unseen objects, including brown dwarfs, black holes, or rogue planets. Large-scale surveys monitored millions of stars over time to capture microlensing events. The MACHO project, conducted in the 1990s, monitored stars in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The project detected some microlensing events, confirming that some fraction of the galactic halo contained compact, faint objects. However, the frequency and mass distribution of these events did not match what would be required for MACHOs to account for all the dark matter. The total contribution from observed MACHOs amounted to only a small percentage of the missing mass. Similar surveys, including the EROS, Experience pour la recherche d'objets sombres, and OGL, Optical Gravitational Lensing Experiment programs, extended these searches. They monitored millions of stars in the Magellanic Clouds and the galactic bulge over years, providing statistically significant limits. These experiments consistently showed that MACHOs, including brown dwarfs, low-mass stars, and black holes, cannot account for the majority of dark matter. The observed microlensing events corresponded to a fraction of the required halo mass, typically less than 20%, far below the total inferred from galaxy rotation curves and cluster dynamics. Brown dwarfs remain an interesting but insufficient candidate. Surveys in infrared, which detect the faint thermal radiation emitted by these objects, have identified thousands of brown dwarfs in the Milky Way. Their masses, distribution, and number density indicate they are common, but not abundant enough to explain the gravitational anomalies attributed to dark matter. Even if every brown dwarf in the galaxy contributed to the halo, their combined mass falls short of what is needed. Black holes were also considered as potential dark matter candidates. Stellar mass black holes, formed from collapsed massive stars, are numerous but limited in total mass. Intermediate mass and primordial black holes, hypothetical black holes formed in the early universe, were suggested as alternative candidates. Observational constraints, including microlensing surveys and the dynamics of wide binary stars, indicate that black holes of these types cannot dominate the massive galactic halos. In addition, searches for X-ray emission from accretion onto black holes have failed to find sufficient numbers to account for the required mass. Rogue planets, unbound planets drifting through interstellar space, have been detected in increasing numbers. Surveys of young star-forming regions show that planet formation is efficient, and some planets are ejected during the early stages of planetary system evolution. However, even assuming large populations of rogue planets, their total mass is far too small to match the inferred halo mass of galaxies. Microlensing surveys detect some of these objects, but the rates are too low to provide the missing mass. The failure of MACOs to account for dark matter became a turning point. It forced astronomers to consider other possibilities beyond ordinary baryonic objects. The logic is straightforward. If all faint stars, brown dwarfs, black holes, and rogue planets cannot explain the gravitational effects seen in galaxies and clusters, the remaining mass must be of a different type. Dark matter cannot be made primarily of ordinary matter that fails to emit light. It must be non-luminous and fundamentally different from the stars and planets observed. Gravitational microlensing experiments provided precise quantitative limits. The MACHO project and similar surveys established upper bounds on the fraction of galactic halos composed of objects with masses between a small fraction of the Sun's mass and several solar masses. These bounds consistently showed that less than about 20% of the halo could consist of MACHOs. Combined with stellar surveys, infrared detections, and dynamical constraints, the conclusion became clear. The dark matter dominating galaxies and clusters cannot be composed of any type of faint or compact baryonic object. The inability of MACOs to explain dark matter also aligns with the distribution of mass in galaxies. The rotation curves measured in spiral galaxies are smooth and extend far beyond the visible disk. MACHOs, being discrete objects, would produce a more uneven distribution of gravitational effects if they dominated the halo. The observed gravitational potential is smooth, indicating a mass component distributed over large volumes, unlike the clumped nature of stars, black holes, or planets. Further evidence against MACHOs comes from galaxy cluster observations. The motions of galaxies in clusters, as first measured by Fritz Zwicky, require a smooth and extended mass component. If compact objects were responsible, their gravitational effects would be more localized, and the virial equilibrium of clusters would not match observations. Surveys of X-ray emitting hot gas in clusters confirm that the majority of mass is not associated with stars, galaxies, or compact baryonic objects. The combination of microlensing surveys, infrared searches, stellar population studies, and cluster dynamics provides a consistent picture. MACOs, including brown dwarfs, faint stars, black holes, and rogue planets, account for only a minor fraction of the mass inferred from gravitational measurements. They cannot explain the flat rotation curves of galaxies, the velocity dispersion in clusters, or the large-scale distribution of matter observed in the universe. Eliminating MACOs as a primary candidate narrows the field for the nature of dark matter. The study of MACOs also established important methodologies for detecting dark, unseen mass. Gravitational microlensing remains a key tool for identifying objects that emit little or no light. Microlensing observations, combined with spectroscopic and infrared surveys, allow astronomers to quantify the number and mass distribution of faint objects. These techniques provided robust evidence that ordinary but faint baryonic objects cannot account for the majority of missing mass. The elimination of MACOs highlights an important principle in the study of dark matter. ruling out alternatives is as critical as identifying candidates. Establishing what dark matter is not builds a foundation for understanding what it must be. By systematically testing faint stars, brown dwarfs, black holes, and rogue planets, astronomers demonstrated that these options are insufficient. The gravitational effects seen in galaxies and clusters require a different type of mass, one that interacts with gravity but not with light in any detectable way. The findings of the MACHO project, EROS and OGIL remain benchmarks in the study of baryonic alternatives. The measured rates of microlensing events, combined with theoretical models of halo composition, place strict limits on the contribution of compact objects. These constraints apply across multiple mass ranges and spatial distributions. They show that the dark matter problem cannot be solved by invoking undetected ordinary objects, even in extreme abundance. Brown dwarfs, black holes, and rogue planets are still studied as part of galactic populations, but their contribution to total mass is small. Surveys of nearby stars, globular clusters, and galactic halos continue to detect these objects, but they collectively fail to produce the gravitational potential required to match rotation curves or cluster dynamics. Dark matter exists on scales far beyond what can be explained by these objects. Ultimately, the elimination of MACHOs shifted the focus toward non-baryonic candidates, particles that do not interact with light, that do not form stars or planets, and that exist throughout galactic halos became the leading explanation. Weakly interacting massive particles, WIMPs, sterile neutrinos, and other hypothetical particles emerged as plausible candidates. This shift reflects the accumulation of evidence showing that ordinary matter cannot account for the missing mass. Ruling out MACHOs also influenced the design of experiments searching for dark matter. Underground detectors, sensitive to rare particle interactions, were developed to detect non-luminous matter. Space telescopes and collider experiments expanded the search to identify particles that could constitute dark matter. The failure of MACHOs to explain gravitational effects provided the rationale for these new approaches, emphasizing the need to look beyond visible or faint ordinary matter. The limits established by microlensing and other surveys also constrain theoretical models of galaxy formation. Simulations that include only baryonic matter cannot reproduce the observed rotation curves, the stability of spiral galaxies, or the mass distribution in clusters. Incorporating a smooth, massive, non-luminous component allows models to match observations. These models rely on dark matter as a fundamental ingredient, consistent with the elimination of MACHOs as a solution. In addition, the distribution of dark matter inferred from galaxy rotation curves and cluster dynamics does not align with the distribution of ordinary baryonic objects. Faint stars, brown dwarfs, and black holes are concentrated in disks and bulges, whereas dark matter halos extend far beyond the visible regions. The spatial mismatch further demonstrates that MACHOs cannot account for the dominant mass component in galaxies. Not normal, baryonic matter. Even after ruling out dim stars, brown dwarfs, black holes, and rogue planets, the question remained: could dark matter simply be ordinary matter that is not luminous? Ordinary matter, known as baryonic matter, includes protons, neutrons, and the atoms that make up stars, planets, gas, and dust. It interacts through electromagnetic forces, emits and absorbs light, and follows the laws of chemistry and nuclear physics. Testing whether dark matter could be baryonic requires examining the universe at its earlier stages and comparing predictions with observations. One of the strongest constraints comes from the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur. During this period, known as Big Bang nucleosynthesis, the first light elements, hydrogen, helium, and traces of lithium and deuterium, formed. The relative abundances of these elements depend sensitively on the density of baryons in the universe. More baryonic matter leads to more collisions among protons and neutrons, producing different proportions of helium and deuterium. Conversely, lower baryon densities yield different abundances. By measuring these primordial abundances today, it is possible to determine the total density of ordinary matter. Observations of helium and deuterium in ancient gas clouds, which have remained largely untouched since the early universe, provide precise measurements of these abundances. Deuterium, in particular, is sensitive to baryon density because it is easily destroyed in stars. Gas clouds in distant galaxies show deuterium to hydrogen ratios that match predictions for a baryon density far below what would be required for all the dark matter. Helium abundances observed in the oldest galaxies also align with these calculations. Lithium presents some discrepancies, but overall the pattern is consistent. The universe contains only enough baryonic matter to account for roughly 5% of its total mass energy content. These constraints from nucleosynthesis indicate that even if all possible faint or unseen baryonic matter were included, it could not make up the 85% of the universe inferred from gravitational effects. Ordinary matter is simply insufficient. The calculations leave a substantial mass deficit that must be explained by something entirely different. Further confirmation comes from the cosmic microwave background, the radiation left over from the Big Bang. The CMB provides a snapshot of the universe roughly 380,000 years after its formation, when the plasma cooled enough for photons to travel freely. The tiny temperature fluctuations in the CMB encode information about the density and composition of the universe. Satellites have measured these fluctuations with extraordinary precision. WMAP, launched in the early 2000s, and Planck, launched in 2009, mapped the CMB across the entire sky, providing detailed power spectra of the fluctuations. The CMB power spectrum contains a series of peaks that correspond to acoustic oscillations in the early plasma. The height and position of these peaks depend on the relative amounts of baryonic matter, dark matter, and dark energy. Observations show that ordinary baryonic matter contributes only a small fraction of the total density, in agreement with nucleosynthesis constraints. Most of the matter influencing the oscillations must be non-baryonic, invisible, and interacting primarily through gravity. These measurements provide independent evidence that dark matter cannot be normal matter. In addition to nucleosynthesis and the CMB, large-scale structure formation offers another test. Galaxies and clusters form from small density fluctuations in the early universe. Ordinary matter interacts with radiation, experiencing pressure that slows the collapse of fluctuations. Dark matter, which does not interact with light, collapses more efficiently, seeding the formation of galaxies and clusters. Simulations that include only baryonic matter fail to produce the observed distribution and clustering of galaxies. Only models that include a substantial non-baryonic component match the large-scale structure of the universe. The evidence from the CMB, nucleosynthesis, and galaxy formation converges on the same conclusion. Ordinary matter, even when accounting for faint or unseen objects, cannot account for the total gravitational mass inferred from galaxy rotation curves, cluster dynamics, and large-scale structure. Dark matter is fundamentally non-baryonic. Its properties differ from those of protons, neutrons, and electrons. It does not emit, absorb, or reflect light. It does not participate in nuclear reactions under normal conditions. Yet it dominates the mass of galaxies and clusters, shaping the evolution of the universe on every scale. Planck satellite measurements provide the most precise numbers. Analysis of the temperature and polarization of the CMB shows that baryonic matter contributes about 4.9% of the universe's total energy density. Dark matter contributes about 26.8%, while dark energy makes up the remainder. These percentages are consistent with independent measurements from nucleosynthesis and gravitational lensing. The universe is mostly composed of invisible matter and energy, with ordinary matter forming only a small component. Constraints on baryonic matter also come from surveys of galaxies and clusters. Observations of stars, gas, and dust indicate that most of the visible mass has been accounted for. Intergalactic gas, detected through X-rays and absorption lines, adds additional mass, but still falls short. The total baryonic content, including stars, planets, and gas, aligns with predictions from nucleosynthesis and the CMB. There is simply not enough ordinary matter to explain the gravitational effects observed in galaxies and clusters. Another argument comes from the behavior of galaxy clusters. Measurements of X-ray emitting gas in clusters reveal that the hot gas alone contains more mass than the stars, but the total still cannot account for the gravitational potential required to keep clusters bound. Weak gravitational lensing maps, which measure the bending of light from background galaxies, indicate the presence of much more mass than is visible or detectable as baryonic matter. The mismatch cannot be resolved by invoking undetected ordinary matter. It points to a dominant non-baryonic component. Attempts to explain dark matter as baryonic also conflict with observations of the intergalactic medium. Absorption lines in the spectra of distant quasars trace gas clouds along the line of sight, providing a census of baryons in the universe. The total baryonic mass inferred from these measurements matches the fraction derived from nucleosynthesis and the CMB, leaving no room for additional baryonic matter sufficient to account for dark matter. The combination of these lines of evidence builds a strong case. Big Bang nucleosynthesis establishes the maximum density of baryons allowed in the universe. The cosmic microwave background confirms that baryonic matter is only a small fraction of the total density. Observations of galaxies, clusters, and the intergalactic medium match these limits. Gravitational effects exceed what can be explained by ordinary matter. Together, these observations demonstrate that dark matter must be non-baryonic. This distinction has profound implications for particle physics and cosmology. Non-baryonic dark matter must consist of particles that do not interact electromagnetically, that are stable on cosmological timescales, and that cluster gravitationally to form halos around galaxies. Leading candidates include weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. These hypothetical particles interact with normal matter only rarely, which is why they remain undetected despite their abundance. The evidence also constrains the density and distribution of dark matter. Its gravitational influence dominates the outer regions of galaxies, stabilizes rotation curves, and shapes the dynamics of galaxy clusters. Dark matter is smoothly distributed over large scales, forming halos around galaxies and permeating the cosmic web. Its presence is inferred from gravitational effects at multiple scales, from individual galaxies to the larger structures in the universe. Understanding that dark matter is non-baryonic allows researchers to focus on detecting it through non-traditional means. Experiments use highly sensitive detectors to search for rare interactions between dark matter particles and ordinary matter. Underground laboratories shielded from cosmic radiation, cryogenic detectors measuring tiny energy deposits, and space-based observatories searching for annihilation signals all aim to capture evidence of these elusive particles. Collider experiments attempt to create dark matter particles in high-energy collisions. Each experiment is informed by the knowledge that dark matter is not made of stars, planets, or ordinary atoms, narrowing the range of possibilities. The non-baryonic nature of dark matter also explains why it dominates cosmic structure formation. Ordinary matter interacts with photons in the early universe, experiencing pressure that slows the growth of fluctuations. Non-baryonic matter, unaffected by radiation, begins collapsing earlier, providing the gravitational scaffolding on which galaxies and clusters form. Without non-baryonic dark matter, simulations of structure formation fail to reproduce the observed universe. The elimination of baryonic matter as a candidate reinforces the uniqueness of dark matter. It cannot be observed through light, it does not emit radiation, and it does not participate in chemistry or nuclear reactions. Its presence is inferred solely from gravity, yet it shapes the evolution of the universe from the earliest times to the present. All observations converge on the conclusion that ordinary matter contributes only a small fraction of total mass, leaving dark matter as a separate, dominant component. The combination of nucleosynthesis, cosmic microwave background measurements, intergalactic gas surveys, gravitational lensing, and galaxy dynamics creates a comprehensive picture. Ordinary matter accounts for roughly 5% of the universe. The remaining mass in galaxies and clusters, plus the structure of the universe itself, requires dark matter that is non-baryonic. Any model of the universe, galaxy formation, or cosmic evolution must include this invisible component to match observations. Planck satellite results continue to refine these measurements, providing increasingly precise values for baryon density, dark matter density, and dark energy. The consistency between Planck nucleosynthesis predictions and large-scale observations confirms that dark matter is non-baryonic and dominates the matter content of the universe. This framework guides current and future research, focusing on particle properties, detection methods, and the role of dark matter in cosmology. The recognition that dark matter is non-baryonic also frames the questions being asked today. What is it made of? How does it interact, if at all, with normal matter beyond gravity? How does it influence the formation and evolution of galaxies and clusters? Understanding its non-baryonic nature narrows the possibilities, enabling experiments and observations to target specific particle properties and distributions. Dark matter's non-baryonic character explains why it has remained undetected for so long. Unlike stars or gas, it does not emit light, absorb radiation, or interact strongly with ordinary matter. Its influence is evident only through gravitational effects, from the motion of stars in galaxies to the bending of light in clusters and the pattern of fluctuations in the cosmic microwave background. Not a mistake in gravity? The motion of stars in galaxies presents a puzzle that cannot be ignored. Stars far from the galactic centre orbit as quickly as those near the centre, defying the expectations set by Newtonian gravity and the visible mass of galaxies. If the laws of gravity and motion are applied as understood from Earth and the solar system, galaxies should fly apart at their edges. The gravitational pull from stars, gas and dust alone, is insufficient to keep them bound. The most common explanation is that an invisible form of mass, dark matter, provides the extra gravity needed. However, an alternative approach emerged in the 1980s, suggesting that perhaps gravity itself behaves differently on galactic scales. Mordechai Milgram, an Israeli physicist, introduced this idea in the early 1980s. Observing the flat rotation curves of galaxies, he proposed a modification to Newton's laws, known as modified Newtonian dynamics, or MOND. The core idea is simple. The force of gravity, or the acceleration it produces, may not follow the same rules at extremely low accelerations, such as those found in the outskirts of galaxies. Below a certain threshold, acceleration does not decrease in the manner predicted by Newton's inverse square law. Instead, it transitions to a different regime, producing stronger than expected acceleration at the edges of galaxies. MOND was motivated by a straightforward observation. The rotation curves of spiral galaxies are remarkably uniform. Stars orbit at roughly the same speed over vast distances, even where visible matter becomes sparse. Standard Newtonian dynamics predicts that orbital velocity should drop off with distance from the centre, analogous to how planets orbit the Sun, more slowly the further out they are. Yet galaxies do not behave like planetary systems. Milgrom asked a simple question. What if the law of gravity itself changes when acceleration falls below a tiny value, about 1.2 times 10 to the power of minus 10 meters per second squared? At these low accelerations, characteristic of galactic outskirts, the gravitational force would not diminish as rapidly, naturally explaining the flat rotation curves without invoking dark matter. MOND succeeds in several notable ways. On the scale of individual spiral galaxies, the theory reproduces observed rotation curves with remarkable accuracy. Using only the distribution of visible matter, MIND predicts the orbital velocities of stars from the inner bulge to the outermost disk. Unlike dark matter models, which require fitting parameters for the mass and distribution of an unseen halo, MIND's predictions depend solely on the observed baryonic content of the galaxy. In many cases, this produces striking agreement with measurements. Low surface brightness galaxies, which are dominated by weak gravitational fields, are particularly well modelled by MOND. The velocity profiles of these galaxies follow the exact patterns predicted by the modified acceleration law. This is the regime where MOND shines, where the acceleration is far lower than anything found in the solar system, and Newtonian dynamics would otherwise predict declining orbital speeds. The simplicity of MOND on galactic scales is part of its appeal. It eliminates the need for an unseen mass component and explains why the Tully-Fisher relation, a correlation between the luminosity of a galaxy and its rotation velocity, holds so consistently. In the MOND framework, the rotation speed is determined directly by the baryonic mass, producing the observed relation naturally. This agreement with empirical scaling laws is difficult to reproduce with dark matter models without fine-tuning. MOND provides a coherent picture for galaxies, requiring no invisible matter, just a modification of the law governing acceleration at low values. However, MOND is not a complete solution to the dark matter problem. On larger scales, such as galaxy clusters, the theory struggles to account for the observed gravitational effects. Clusters of galaxies contain far more mass than the stars alone can explain. Observations of galaxy velocities within clusters, along with measurements of hot gas emitting X-rays, reveal that there is still missing mass even when MOND is applied. The acceleration at cluster scales is often above or near the MOND threshold, yet the predicted gravitational pull from visible matter is insufficient. MOND requires some additional unseen mass in clusters, effectively reintroducing dark matter in a different form. The cosmic microwave background, the relic radiation from the Big Bang, presents an even more serious challenge. The CMB contains patterns of temperature fluctuations that encode the distribution of matter and energy in the early universe. The heights and positions of the acoustic peaks in the CMB power spectrum depend on the relative amounts of baryonic matter, dark matter, and radiation. MOND alone, modifying only Newtonian gravity at low accelerations, cannot reproduce the observed CMB spectrum. The fluctuations indicate a significant non-baryonic mass component, contributing to gravitational wells that affect photon propagation in the early plasma. The absence of this component in MOND-based models results in discrepancies with measurements from WMAP and Planck. Colliding galaxy clusters provide another strong argument against MOND as a universal explanation. The Bullet cluster, for instance, shows two clusters that have passed through one another. X-ray observations reveal the hot gas, which carries most of the baryonic mass, lagging behind the galaxies due to drag and friction. Gravitational lensing measurements map the total mass distribution and reveal that the majority of mass is not coincident with the gas. The mass peaks align with the galaxies, indicating the presence of a substantial, invisible component. MOND cannot account for this separation between baryonic matter and total gravitational mass. Even when modified dynamics is applied, additional unseen matter is required to reproduce the lensing data. Attempts to extend MIND into a relativistic framework, such as TVES, tensor vector scalar gravity, have addressed some limitations. These theories introduce additional fields to reconcile MIND with general relativity, allowing for lensing effects and cosmological evolution. While TVS can reproduce certain galaxy-scale observations, it still faces challenges with large-scale structure and the CMB. Matching the full range of cosmological data requires the introduction of additional components that resemble dark matter, diminishing the original simplicity of a MIND. Another limitation arises from dwarf galaxies and satellite systems. Observations of ultra-faint dwarf galaxies orbiting the Milky Way reveal extremely high mass-to-light ratios. The stars in these systems move in ways that require much more gravitational mass than is observed. MOND predicts certain velocity dispersions based on the baryonic content, but in some cases, the predicted velocities differ from measurements. While MOND can often fit these galaxies by adjusting parameters or considering external field effects, the fits are less natural than on spiral galaxy scales. Despite these limitations, MIND has had a significant impact on astrophysics. It demonstrates that the empirical regularities of galactic rotation curves are not trivial and may point to new physics. The precise correlation between baryonic mass and orbital velocity, captured by Mond's acceleration law, is a real phenomenon that any complete theory of dark matter must account for. In this sense, MOND has influenced the development of models that incorporate both dark matter and baryonic physics, leading to hybrid approaches that combine particle dark matter with empirical galactic scaling relations. MIND also emphasizes the need to test fundamental assumptions about gravity. While Newtonian and Einsteinian gravity are well verified within the solar system and in strong gravitational fields, the weak field regime in galaxies is far less constrained. MOND challenges researchers to examine the limits of these laws and consider how modifications might manifest at low accelerations. The theory encourages precision measurements of rotation curves, velocity dispersions, and gravitational lensing in diverse galactic systems. These observations, in turn, refine the properties that any candidate for dark matter must satisfy. In the decades since MIND was proposed, extensive data have accumulated across multiple scales: spiral galaxies, dwarf galaxies, clusters, and large-scale structure provide stringent tests. On galactic scales, a MIND reproduces rotation curves and scaling laws with remarkable accuracy, often outperforming simple dark matter halo models in terms of direct predictability. On cluster and cosmological scales, however, MIND alone is insufficient, requiring either additional mass or extensions to the theory. These successes and failures make MIND a tool for understanding the distribution of mass and the interplay between baryons and dark matter, even if it does not replace dark matter entirely. In galaxy clusters, the discrepancy between visible mass and observed dynamics remains a robust argument for non-baryonic dark matter. While MIND reduces the gap compared to Newtonian predictions, it does not eliminate it. Clusters contain thousands of galaxies and vast amounts of hot gas, and the gravitational potential inferred from galaxy velocities and lensing exceeds what MIND predicts using only baryons. These observations reinforce the conclusion that at larger scales, unseen mass is necessary. The smoking gun: gravitational lensing. In 1915, Albert Einstein introduced a new way of understanding gravity that completely changed physics. Before this, gravity was understood through Isaac Newton's laws as a force that pulls objects toward each other across empty space. Newton's theory worked extremely well for planets, moons, and objects on Earth, and it allowed scientists to predict planetary motion with impressive accuracy. However, Einstein proposed something deeper and more radical. He argued that gravity is not a force in the usual sense, but a result of space and time being curved. According to his theory of general relativity, massive objects such as stars and galaxies bend the fabric of space-time around them, and other objects move along the curved paths created by that bending. To understand this idea, imagine space not as a simple, empty stage where events take place, but as something that can stretch and curve. When a massive object like the Sun exists in space, it changes the geometry around it. The Earth moves around the Sun not because it is being pulled by an invisible rope, but because it is following the curved shape of space-time created by the Sun's mass. In this picture, gravity is geometry. Objects move along the straightest possible paths in curved space, and those paths appear to us as orbits. One of the most important predictions of general relativity was that light would also follow these curved paths. Under Newton's view, light has no mass, and therefore should not be affected much by gravity. Under Einstein's view, light travels through space-time, and if space-time is curved, then the path of light must bend when it passes near a massive object. This bending would not happen because light is being pulled in the normal sense, but because the space through which it travels is curved. This prediction was tested during a total solar eclipse in 1919. During an eclipse, the moon blocks the bright light of the sun, allowing distant stars near the sun's position in the sky to become visible. Scientists measured the positions of those stars and compared them to their normal positions when the sun was elsewhere in the sky. The results showed that the starlight had shifted slightly, exactly in the way Einstein's equations predicted. The light from distant stars had bent as it passed near the sun. This observation made Einstein famous and confirmed that space-time is curved in the presence of mass. At the time, the bending of starlight near the sun was a small effect. However, the real power of gravitational lensing became clear decades later, when astronomers began studying galaxies and clusters of galaxies. A single star like the Sun bends light only slightly because its mass is limited. A galaxy contains billions of stars, along with gas and dust, and a galaxy cluster contains hundreds or thousands of galaxies. The total mass in these systems is enormous, and therefore the curvature of space-time around them is much stronger. When light from even more distant galaxies passes through this curved region, the bending can be dramatic. This effect is called gravitational lensing because the massive object acts like a lens. Unlike a glass lens that bends light due to changes in material, a gravitational lens bends light due to curved space-time. If a distant galaxy sits behind a massive cluster, from our point of view, the light from that distant galaxy will not travel in a straight line. Instead, it will curve around the cluster, and the image we see may be stretched, distorted, or even multiplied. In some cases, this bending creates long bright arcs around a galaxy cluster. These arcs are not artistic illusions or computer drawings. They are real galaxies whose images have been stretched into curved shapes. In cases of nearly perfect alignment, the background galaxy can appear as a full ring around the cluster, known as an Einstein ring. The exact shape and position of these arcs depend on the total mass of the lensing object and how that mass is distributed. The critical point is that gravitational lensing depends only on mass, not on light. A lensing mass does not need to shine. It does not need to emit radiation. It only needs to have gravity. If something has mass, it will curve space-time, and curved space-time will bend light. This makes gravitational lensing a direct way to measure mass in the universe, regardless of whether that mass is visible. Astronomers use two main types of lensing to study mass: strong lensing and weak lensing. Strong lensing produces obvious distortions such as arcs, rings, and multiple images of the same background galaxy. Weak lensing is more subtle and requires careful statistical analysis. In weak lensing, background galaxies appear slightly stretched in a consistent direction. Any single galaxy might look normal. But when thousands or millions of galaxies are analysed together, patterns emerge. These patterns reveal how space-time is curved across large regions of the sky. Using these techniques, astronomers create mass maps of galaxy clusters and large sections of the universe. These maps show where mass must be located in order to produce the observed distortions. What they found was unexpected and striking. The mass distribution revealed through lensing often does not match the distribution of visible matter. The regions where light bends most strongly contain far more mass than can be accounted for by stars and gas alone. Galaxy clusters contain large amounts of hot gas that glow in X-rays, and this gas can be observed with space telescopes. The gas often contains more visible mass than the galaxies themselves. Even when astronomers add together the mass of all the stars and all the hot gas, the total still falls far short of what is needed to produce the observed lensing effects. The bending of light demands much more mass than what shines. The mathematics of gravitational lensing is strict and based on Einstein's equations. The amount of bending depends on the mass and the geometry of the system. When astronomers observe multiple images of the same background galaxy, they can calculate the mass required to produce those images. These calculations repeatedly show that the total mass is several times larger than the visible mass. The extra mass forms an extended halo around the cluster, spreading far beyond the bright galaxies. This halo does not emit light, does not glow in X-rays, and does not absorb radiation in a detectable way. Yet it clearly bends light. The presence of this invisible mass is not inferred from the motion of stars or galaxies alone. It is directly measured through the curvature of space-time. Light from distant galaxies physically changes direction as it travels toward Earth, and that change in direction encodes the amount of mass along its path. Gravitational lensing has also been used to map mass on even larger scales, revealing a vast cosmic web of structure. Galaxies are arranged along long filaments of matter, with large empty regions between them. Weak lensing surveys measure tiny distortions across huge areas of the sky and reconstruct the distribution of mass across billions of light years. These maps show dense clumps and filaments of mass even in places where relatively few visible galaxies are present. The power of lensing lies in its independence from assumptions about how matter behaves. It does not rely on measuring how fast stars move or how hot gas is. It does not depend on theories of galaxy formation. It depends only on the geometry of space-time and the path of light. When light bends more than visible matter allows, the extra mass must exist. The bullet cluster. In the universe, galaxy clusters are the largest structures held together by gravity. Each cluster contains hundreds or even thousands of galaxies, along with enormous clouds of extremely hot gas that fill the space between them. This gas reaches temperatures of tens of millions of degrees and shines brightly in X-rays. When astronomers look at a cluster using optical telescopes, they see galaxies as small bright islands of stars. When they observe in X-ray light, they see glowing clouds of hot gas that often contain more ordinary matter than the galaxies themselves. For a long time, measurements of how fast galaxies moved inside clusters showed that the visible matter was not enough to hold the clusters together. Gravitational lensing later confirmed that much more mass was present than what could be seen. One particular system changed the debate in a dramatic way. It is known as the bullet cluster. This system is actually two galaxy clusters that have collided with each other at extremely high speed. The collision happened hundreds of millions of years ago, and what astronomers observe today is the aftermath of that violent event. To understand why this cluster is so important, it helps to understand what happens during a cluster collision. A galaxy cluster contains three main components: galaxies made of stars, hot gas filling the space between galaxies, and whatever invisible mass holds the cluster together. When two clusters move toward each other and collide, these components behave differently because they interact in different ways. galaxies are mostly empty space. Although they contain billions of stars, the stars are separated by vast distances. When two clusters collide, the galaxies mostly pass through each other without direct collisions between stars. The chance of two stars hitting each other is extremely small. As a result, the galaxies move forward with only slight disturbance. The hot gas behaves very differently. Gas clouds are not empty space. They are made of charged particles that interact strongly when they collide. When the two clusters in the bullet cluster system pass through each other, their hot gas clouds slam together. The gas experienced friction and pressure, which slowed it down. This created a shock wave, similar to the shock wave formed when a jet breaks the sound barrier. In X-ray images, this shock front appears as a bright, curved edge, giving the system its name because it looks like a bullet moving through material. Now comes the crucial observation. Astronomers mapped the visible matter in the bullet cluster using optical telescopes for galaxies and X-ray telescopes for the hot gas. Most of the ordinary matter in clusters is in the hot gas, not in the stars. After the collision, the gas was left behind in the center region where the impact occurred, slowed down by friction. The galaxies moved ahead on both sides. If gravity were controlled only by visible matter, then the center region filled with hot gas should contain most of the gravitational mass. The strongest gravitational pull should be located where the gas is densest. However, gravitational lensing measurements told a completely different story. Using weak lensing techniques, astronomers measured the distortions of background galaxies behind the bullet cluster. They analyzed the slight stretching of thousands of distant galaxies and reconstructed a mass map. This map showed where spacetime was most strongly curved. The surprising result was that the peaks of gravitational mass were not located where the hot gas was. Instead, the strongest mass concentrations were aligned with the galaxies on either side of the collision. This means that most of the mass passed through the collision along with the galaxies, not with the gas. The galaxies themselves do not contain enough visible matter to explain this mass peak. The stars in the galaxies account for only a small fraction of the required mass. Therefore, a large amount of invisible mass must have traveled with the galaxies and continued moving forward without slowing down. The separation between visible matter and gravitational mass is clearly visible in combined images. X-ray maps show the hot gas concentrated in the middle. Optical images show galaxies on either side. Lensing maps show mass centered around the galaxies, not the gas. There is a clear offset between the location of most of the ordinary matter and the location of most of the total mass. This observation is extremely important because it shows that mass exists in a form that does not interact strongly with normal matter. The hot gas slowed down because it interacts through electromagnetic forces. The invisible mass did not slow down in the same way. It passed through the collision with very little interaction, behaving as if it only interacts through gravity. If dark matter did not exist and gravity was simply wrong on large scales, as proposed in modified Newtonian dynamics, then the gravitational field should still follow the visible mass. Mond changes the law of gravity, but does not introduce new mass. Under Mond, the gravitational pull should be strongest where the baryonic matter is located. In the bullet cluster, that would mean the strongest lensing signal should align with the hot gas, since the gas contains most of the ordinary mass. However, the lensing map does not match that expectation. The strongest gravitational effects are centered on regions with relatively little visible matter. This creates a serious problem for Mond. The theory was designed to explain galaxy rotation curves without dark matter, and it performs well in that specific context. However, in a system where ordinary matter has been physically separated from the gravitational mass, modifying gravity alone cannot explain the observation. The gravitational field is not centered on the majority of baryonic matter. Instead, it traces something else. Some extended versions of Mond attempt to address this issue by adding additional fields or even some form of unseen matter. But once additional unseen mass is introduced, the original goal of eliminating dark matter is lost. The bullet cluster demonstrates that there is mass present that behaves differently from ordinary matter during a collision. It does not emit light, it does not glow in X-rays, it does not experience strong drag forces, it moves through collisions almost unaffected. The speed of the collision also provides insight. The two clusters in the bullet cluster system collided at several thousand kilometers per second. The shock wave in the gas reveals the direction and speed of motion. The galaxies and the invisible mass components continued forward while the gas was left behind. This creates a natural experiment in which the components of the cluster have been sorted based on how they interact. Ordinary matter interacts strongly and slows down. Dark matter interacts weakly and continues moving. Gravitational lensing acts as the measuring tool in this experiment. It maps the total mass regardless of its composition. When that map is compared to the distribution of visible matter, the separation becomes undeniable. The mass peaks coincide with the galaxies rather than the gas. The gravitational field is strongest where little luminous matter exists. The bullet cluster is not the only example of such behavior, but it is the clearest and most studied case. Other merging clusters show similar patterns, although not always as cleanly separated. Together, these systems provide strong evidence that dark matter is a real physical component of the universe rather than a mistake in gravity. The importance of this observation lies in its directness. Rotation curves could be explained either by adding dark matter or modifying gravity. The motion of galaxies in clusters could be debated. However, the separation of mass from visible matter during a collision presents a visual and measurable difference that is difficult to dismiss. The gravitational field does not follow the majority of ordinary matter. Instead, it follows an invisible component that behaves as if it interacts only weakly with normal matter. In the bullet cluster, the lensing map effectively shows two ghostly clouds of mass moving ahead of the glowing gas. These clouds have no significant emission of light. They are detected purely through the bending of light from more distant galaxies. This makes the observation deeply connected to Einstein's theory of curved spacetime. The curvature reveals the presence of mass, and that mass does not match the visible material. The system acts as a cosmic laboratory. The collision separated components that are usually mixed together. In a normal cluster, dark matter and baryonic matter overlap, making it harder to see the difference. In the bullet cluster, the collision pulled them apart, exposing the hidden mass directly. This event does not rely on indirect reasoning about motion or temperature. It relies on geometry and observation. Light bends where mass exists. The strongest bending is not where the brightest gas is. The mass has moved independently of the gas. That independence strongly supports the existence of dark matter as a real substance in the universe. The cosmic blueprint, dark matter, and the early universe. Long before the first stars ignited, before galaxies took shape, before planets existed, the universe was a hot, dense sea of light and particles. It was not dark in the beginning, it was blindingly bright. Matter and radiation were tightly linked together in a glowing plasma that filled all space. To understand dark matter, we have to go back to that early time, because the evidence for its existence is written into the oldest light in the universe. That ancient light is called the cosmic microwave background, or CMB. It is the faint afterglow of the Big Bang. It fills the entire sky. It does not come from any star or galaxy. It comes from a time when the universe was only about 380,000 years old. At that early stage, the universe was extremely hot. Electrons and protons move freely, and photons, particles of light, constantly scattered off those charged particles. The universe was opaque, like the inside of a star. Light could not travel far without being scattered. As the universe expanded, it cooled. Eventually, it became cool enough for electrons and protons to combine into neutral hydrogen atoms. When that happened, photons were no longer scattered constantly. They were suddenly free to travel through space. That moment is called recombination. The light released then has been travelling ever since. Today, that light has cooled dramatically because the universe has expanded. What was once visible light is now microwave radiation. It is extremely faint, only about 2.7 degrees above absolute zero, yet it is everywhere. If you tune an old television to static, a small fraction of that noise comes from this ancient radiation. The CMB is not perfectly smooth. It contains tiny temperature variations across the sky. These differences are incredibly small, only about 1 part in 100,000. But they are not random. They contain patterns. Those patterns are the blueprint of everything that formed later. To measure these patterns, scientists launched space missions designed to map the microwave sky with extreme precision. One of the most important was the WMAP, launched in 2001. WMAP mapped temperature differences across the entire sky and revealed detailed structure in the CMB fluctuations. Later, an even more precise mission was launched, Planck. Planck measured both temperature and polarization patterns of the CMB with higher resolution and sensitivity than any previous mission. The data from Planck gave the most accurate picture yet of the early universe. The temperature variations in the CMB are not just random hot and cold spots. They reflect density fluctuations in the early universe. Some regions were slightly denser than average, some were slightly less dense. These fluctuations were tiny, but they mattered enormously. Gravity would later amplify them, turning small overdensities into galaxies and clusters. Before recombination, when the universe was still a plasma, gravity and radiation pressure were locked in a constant struggle. In denser regions, gravity tried to pull matter inward, but photons created pressure that pushed outward. This tug-of-war created oscillations, like sound waves, moving through the plasma. These oscillations are called acoustic oscillations. They left a clear imprint in the CMB. When scientists analyze the temperature variations across the sky, they break the pattern into different scales. This produces a graph known as the power spectrum. The power spectrum shows peaks and valleys. Each peak corresponds to a specific scale of oscillation in the early plasma. The first peak represents regions where compression was strongest at the moment photons were released. The second peak corresponds to regions where rarefaction or expansion was strongest. Higher peaks represent smaller scale oscillations. The height and position of these acoustic peaks depend on the composition of the universe. The amount of normal matter affects how strong the compression was. The amount of dark matter affects how gravity shaped those oscillations. Dark energy affects the geometry of space and the overall expansion. The first peak in the CMB power spectrum tells us about the curvature of the universe. Its position shows that space is very close to flat on large scales. This means the total energy density of the universe is very close to the critical density required for flat geometry. The relative heights of the first and second peaks reveal the amount of baryonic matter, ordinary matter made of protons and neutrons. Baryons add weight to the plasma and enhance compression. If there were more baryons, the odd-numbered peaks would be much higher compared to the even-numbered ones. The measured pattern shows that baryons make up only a small fraction of the total matter. Dark matter influences the peaks differently. Unlike baryons, dark matter does not interact with radiation. It does not feel radiation pressure. That means dark matter began clumping earlier, forming gravitational wells even before recombination. These wells deepen the compression in certain regions and shape the oscillation pattern. When scientists fit models to the CMB power spectrum measured by Planck, the best match requires a universe made mostly of something invisible. The data show that only about 5% of the total energy density is normal matter. around 27% is dark matter. The rest, about 68%, is dark energy. These numbers are not guesses. They come directly from matching theoretical models of the early universe to the precise pattern of acoustic peaks measured in the CMB. Changing the dark matter fraction changes the shape of the power spectrum. Increasing it too much shifts peak positions. Decreasing it too much reduces the fit quality dramatically. The best fitting model consistently includes about 27% dark matter. Another way to see this is through the matter power spectrum. This describes how density fluctuations vary with scale. It shows how much structure exists at different sizes. The matter power spectrum observed in the CMB aligns with later measurements from galaxy surveys, but only when dark matter is included. If the universe contained only normal matter, the pattern of fluctuations would look different. Radiation pressure would have prevented small structures from growing before recombination. After recombination, there would not have been enough time for gravity to amplify those fluctuations into the galaxies and clusters we observe today. Dark matter solves this timing problem. Because it does not interact with radiation, it began forming clumps earlier. These clumps acted as seeds. When normal matter decoupled from radiation, it fell into these pre-existing gravitational wells. The CMB also provides polarization data. Tiny patterns in polarization further confirm the density parameters. These patterns arise from the scattering of photons during recombination and contain information about velocity fields in the plasma. The polarization results from Planck strongly support the same composition numbers derived from temperature data. The consistency is striking. Independent measurements within the CMB agree with each other. Temperature anisotropies, polarization modes, lensing of the CMB itself all converge on the same model. Roughly 5% normal matter, roughly 27% dark matter, roughly 68% dark energy. The dark matter component is required not only for matching peak heights, but also for explaining the lensing of the CMB. As CMB photons travel across billions of light years, their paths are bent by mass along the way. This weak lensing effect slightly smooths the peaks in the power spectrum. Planck detected this smoothing and measured it. The amount of smoothing matches the dark matter fraction inferred from the peaks themselves. This agreement across multiple features strengthens confidence in the result. The early universe leaves no room for large amounts of unseen normal matter. The baryon density is tightly constrained by the peak structure. Any attempt to replace dark matter with extra baryons would destroy the delicate pattern of acoustic oscillations. The CMB acts like a fossil imprint. It preserves the conditions of the universe at a time when it was simple enough to model precisely. The physics involved, gravity, radiation pressure, atomic transitions, are well understood. When these laws are applied to the data, the solution consistently requires a dominant, non-baryonic matter component. This cosmic blueprint shows that dark matter was present long before galaxies existed. It shaped the early density fluctuations. It influenced how acoustic waves propagated in the plasma. It determined how structure would later grow. Structure formation. The tiny fluctuations seen in the cosmic microwave background were not random marks on a map. They were the starting conditions for everything that formed later. Those temperature differences of 1 part in 100,000 represented real density variations in matter. Some regions contained slightly more mass than average. Others contained slightly less. From those almost invisible differences, the entire large-scale structure of the universe emerged. Gravity is simple in principle. Regions with more mass pull in more matter. Over time, this pull amplifies small differences. A slightly denser region becomes denser still. A slightly emptier region loses more material. The process feeds on itself. The question is not whether structure forms. The question is how fast it forms and what controls that speed. If the universe contained only normal matter, structure formation would face a serious problem. Before recombination, normal matter was tightly coupled to radiation. Photons scattered constantly off electrons. Radiation pressure resisted gravitational collapse. Density fluctuations in normal matter could not grow freely. They oscillated as sound waves in the plasma instead of collapsing into clumps. After recombination, radiation decoupled and normal matter was finally free to fall under gravity alone. But the clock was already ticking. The universe had already expanded for 380,000 years. From that point to the formation of the first galaxies, there was limited time. Simulations that include only baryonic matter show that structure would grow far too slowly. Galaxies would not have had enough time to form before the present day. The observed universe is far more structured than a baryon-only model allows. This is where dark matter becomes central. In the standard cosmological model, dark matter does not interact with radiation. It does not feel radiation pressure. That means it decoupled dynamically much earlier. As soon as the universe cooled enough for matter to dominate over radiation in terms of energy density, dark matter began to collapse into gravitational wells. This framework is known as the cold dark matter model, often abbreviated as CDM. Cold does not mean low temperature in the everyday sense. It refers to particle speeds in the early universe. Cold dark matter particles move slowly compared to the speed of light. Slow-moving particles do not erase small-scale fluctuations. They allow structure to grow from small seeds upward. In contrast, if dark matter were hot, meaning highly relativistic in the early universe, its fast motion would smooth out small-scale density fluctuations. Structure would form first on large scales, then fragment downward. Observations do not match that pattern. The universe shows small galaxies as well as large clusters. The distribution of structures favours cold, dark matter. In the CDM model, dark matter halos form first. These halos are gravitationally bound clumps of dark matter. They arise from the amplification of early density fluctuations seen in the cosmic microwave background. As time passes, small halos merge with other halos. Gravity draws them together. This merging process builds larger and larger structures. This growth pattern is called hierarchical structure formation. Small objects form first. They merge to form larger objects. Those larger objects merge into even larger ones. The pattern repeats across cosmic time. Computer simulations play a major role in testing this model. Large numerical simulations track billions of dark matter particles interacting under gravity. Starting from initial conditions based on CMB measurements, these simulations evolve the universe forward in time. The result is a web-like structure known as the cosmic web. The cosmic web consists of filaments, sheets, and voids. Filaments are long strands of matter connecting clusters. Voids are large empty regions with very low density. At the intersections of filaments, massive galaxy clusters form. This pattern appears naturally in cold dark matter simulations. When astronomers map the distribution of galaxies across large volumes of space, they see the same web-like structure. Surveys such as the Sloan Digital Sky Survey have mapped millions of galaxies. The observed large-scale distribution closely matches the predictions of CDM simulations. Dark matter halos are not directly visible. They do not emit light, but their gravitational influence shapes the motion of galaxies and gas. Every galaxy is thought to reside within a dark matter halo. The halo extends far beyond the visible edge of the galaxy. In spiral galaxies, rotation curves remain flat at large radii because stars orbit within these extended halos. In the early universe, once dark matter halos formed, normal matter began to fall into them. Gas cooled through radiation processes. As it cooled, it lost pressure support and settled toward the center of the halo. Over time, the gas became dense enough for nuclear fusion to ignite in its core regions. The first stars formed. These first stars likely formed in small dark matter halos a few 100 million years after the Big Bang. They were probably massive and short-lived. Their radiation began to reionize the universe, stripping electrons from hydrogen atoms again. This epoch is known as reionization. As more halos merged and grew, galaxies assembled. Spiral galaxies formed in halos with significant angular momentum, allowing gas to settle into rotating disks. Elliptical galaxies formed through mergers that disrupted disk structures. Clusters of galaxies formed at the nodes of the cosmic web, where multiple filaments intersect. The growth of structure can be quantified using the matter-power spectrum. This spectrum describes how density fluctuations vary with scale. Observations of galaxy clustering match the power spectrum predicted by CDM, when dark matter makes up roughly 27% of the total energy density. Another line of evidence comes from baryon acoustic oscillations. These are remnants of the same acoustic waves seen in the cosmic microwave background. The preferred scale imprinted in the early plasma remains visible in the distribution of galaxies today. The spacing of galaxies on large scales reflects this characteristic length. Measurements of this scale agree with the parameters derived from the CMB and CDM. Without dark matter, the story changes dramatically. In a universe composed only of normal matter, early density fluctuations would have been suppressed before recombination. After recombination, gravity would start amplifying them, but the growth rate would be too slow. Galaxies would be rare and much less massive. The cosmic web would be far less pronounced. The observed clustering of galaxies would not match predictions. Simulations that remove dark matter show delayed structure formation. Large clusters would not have time to assemble. The distribution of galaxies would be smoother. The contrast between filaments and voids would be weaker. Observational data contradicts this outcome. Dark matter also affects the internal structure of halos. Simulations predict a characteristic density profile, often described through the Navarro-Frank-White profile. This profile shows a dense central region with density decreasing outward. Observations of galaxy rotation curves and gravitational lensing provide evidence consistent with such halo structures, though there remain detailed challenges at small scales. On scales of dwarf galaxies, some tensions exist between simulations and observations, such as the Caucus problem and the missing satellites problem. These issues are areas of active research. Solutions may involve baryonic feedback processes, such as energy injection from supernova explosions redistributing matter within halos, or slight modifications to dark matter particle properties. Despite these small-scale challenges, the large-scale success of CDM remains strong. The timeline of structure formation under CDM unfolds in a clear sequence. First, tiny fluctuations exist in the early universe. Dark matter begins clumping once matter dominates over radiation. Small halos form. Halos merge into larger halos. Gas falls into halos and cools. Stars form within the densest gas regions. Galaxies assemble through merging and accretion. Clusters form at filament intersections. The cosmic web emerges as the dominant pattern. Observations of high redshift galaxies provide further confirmation. Telescopes such as the James Webb Space Telescope observe galaxies less than 1 billion years after the Big Bang. These early galaxies appear in regions where simulations predict early halo formation. Their number density and clustering properties align with expectations from CDM models tuned to CMB data. Gravitational lensing surveys also map the distribution of total matter, not just visible matter. Weak lensing measurements trace the underlying dark matter distribution across large areas of the sky. These maps reveal filamentary structures similar to those seen in simulations. The agreement extends across multiple independent observational techniques. The rate of growth of structure can be measured through redshift space distortions. Galaxies move not only with cosmic expansion, but also toward over-dense regions under gravity. These peculiar velocities distort clustering patterns in redshift surveys. The amplitude of these distortions depends on the amount of matter in the universe. Measurements match the growth rate predicted by a universe with roughly 27% dark matter. Dark matter's role in structure formation is therefore not limited to explaining galaxy rotation curves. It underpins the entire timeline of cosmic evolution from the first fluctuations to present-day clusters. It provides the gravitational scaffolding upon which visible structures assemble. The early universe provided the blueprint in the form of tiny fluctuations in density. Dark matter amplified those fluctuations early, before normal matter could respond freely. This early start allowed enough time for complex structures to form within the age of the universe. Gas physics determines how stars ignite and how galaxies evolve internally, but gravity sets the stage. Dark matter dominates gravity on large scales. Its presence determines how quickly overdense regions collapse and how the cosmic web develops. Remove dark matter from the equations, and the predicted universe becomes sparse and delayed in structure formation. Keep dark matter with the properties of cold, collisionless particles, and the simulations produce a universe that resembles what telescopes observe across billions of light years. What could dark matter be? For decades, measurements of galaxies, clusters, gravitational lensing, and the cosmic microwave background have all pointed toward the same conclusion. Most of the matter in the universe does not emit light and does not absorb light. It moves under gravity, shapes structure, and outweighs ordinary matter by more than 5 to 1. The next question is direct and unavoidable. If it is not made of atoms, what is it made of? One of the most studied possibilities is a class of particles known as WIMPs, short for weakly interacting massive particles. The name is descriptive. Massive means heavier than particles like electrons or neutrinos. Weakly interacting means they do not interact through electromagnetism or the strong nuclear force. Instead, they interact through gravity and possibly through the weak nuclear force. The weak force is one of the 4 known fundamental forces. It is responsible for processes such as radioactive beta decay. Compared to electromagnetism, it is much weaker at low energies and acts over extremely short distances. If dark matter interacts through the weak force, it would rarely collide with normal matter. That matches observations. Dark matter does not glow, does not scatter light, and does not form atoms. The theoretical appeal of WIMPs comes from a concept known as the thermal relic hypothesis. To understand this, it helps to return to the early universe, when temperatures were extremely high and particles constantly collided with one another. In that environment, particles and antiparticles were created and destroyed in rapid succession. If WIMPs existed at that time, they would have been part of this thermal bath. At very high temperatures, collisions between energetic particles could create WIMP pairs. At the same time, WIMPs could annihilate with one another, converting back into lighter particles. As long as the universe was dense and hot, creation and annihilation rates stayed in balance. The number of WIMPs remained close to an equilibrium value determined by temperature. As the universe expanded, it cooled. When the temperature dropped below the mass energy of the WIMP, producing new WIMPs through collisions became rare. Annihilation continued, reducing their number. Eventually, the universe expanded enough that WIMPs became too spread out to find one another efficiently. At that point, annihilation slowed dramatically. The remaining WIMPs stopped interacting frequently, and their number per volume effectively froze. This moment is known as freeze-out. The key idea in the thermal relic hypothesis is that the present-day abundance of WIMPs depends on how strongly they interacted in the early universe. If their annihilation cross-section was large, they would have annihilated more efficiently, leaving behind fewer relic particles. If their cross-section was small, more of them would survive. When physicists calculate the relic abundance using standard cosmology and assume an interaction strength similar to the weak nuclear force, something remarkable happens. The predicted leftover density is close to the observed dark matter density. This numerical coincidence is often called the WIMP miracle. It suggests that a particle with weak-scale interactions and a mass in the range of roughly tens to thousands of Geiger electron volts would naturally produce the right amount of dark matter today. The weak interaction scale corresponds to energies around 100 Geiger electron volts. That scale is not arbitrary. It appears in the standard model of particle physics in processes involving the W and Z bosons. The idea that dark matter might live near that same scale links cosmology with particle physics in a direct way. Many extensions of the standard model predict new particles with properties similar to WIMPs. Supersymmetry, for example, introduces partner particles for each known particle. In several supersymmetric models, the lightest supersymmetric particle is stable and interacts weakly, making it a strong WIMP candidate. Other theories involving extra dimensions or new gauge symmetries also produce WIMP-like particles. The WIMP scenario makes clear predictions. If WIMPs exist, they should still be present in large numbers today, moving through galaxies and through Earth itself. Although they rarely interact with normal matter, their sheer abundance means that occasionally one should collide with an atomic nucleus. This leads to the strategy known as direct detection. Experiments are built deep underground to shield them from cosmic rays and other background radiation. The goal is to observe the tiny recoil of a nucleus after being struck by a passing WIMP. Two of the most sensitive experiments operating today are LUX-ZEPPELIN and Xenon-NT. Both use large volumes of ultra-pure liquid xenon as the detection medium. Liquid xenon is chosen for several reasons. It is dense, which increases the probability of interaction. It produces both light and electrical signals when a nucleus recoils. It can be purified to extremely low levels of radioactive contamination. In these detectors, a WIMP collision would produce a brief flash of ultraviolet light and free electrons. Sensors detect the light and measure the drift of electrons in an electric field, allowing reconstruction of the event. These experiments are located deep underground to reduce background noise from cosmic rays. LUX-ZEPPELIN operates nearly a mile below the surface in a former gold mine in South Dakota. Xenon-NT operates deep beneath a mountain in Italy's Gran Sasso laboratory. Rock overhead absorbs most cosmic radiation, allowing the detectors to search for extremely rare events. Background control is critical. Natural radioactivity in surrounding materials, trace contaminants in the xenon, and even neutrinos from the Sun can mimic signals. Researchers use careful shielding, material selection, and statistical analysis to distinguish possible WIMP events from background noise. The sensitivity of these detectors is often described in terms of the WIMP nucleon cross-section. This value represents the probability that a WIMP will scatter off a nucleus. Experiments report upper limits on this cross-section for various assumed WIMP masses. Over the past decade, the sensitivity has improved dramatically. Each new generation of detectors increases the target mass and reduces background. As of now, neither LUX-ZEPPELIN nor Xenon-NT has reported a confirmed detection of WIMPs. Instead, they have placed some of the strongest limits yet on the interaction cross-section. These limits shrink the allowed parameter space for WIMPs. Parameter space refers to the range of possible masses and interaction strengths that remain consistent with both cosmological abundance and experimental non-detections. Early on, there was a wide region where WIMPs could plausibly exist. With each null result, that region becomes smaller. For example, if WIMPs had masses around tens of giga-electron volts and interaction strengths near the weak scale, Many of those possibilities are now excluded. Experiments have ruled out cross-sections down to extremely small values, far below what was originally expected from the simplest WIMP miracle calculations. However, the parameter space is not fully closed. WIMPs could have weaker interactions than initially assumed. They could have masses outside the most sensitive ranges of current detectors. Some models predict suppressed scattering rates that would make direct detection extremely challenging. Another approach is indirect detection. If WIMPs can annihilate with one another, then in regions of high dark matter density, such as the centers of galaxies, annihilation might produce gamma rays or other particles. Telescopes search for excess signals that could indicate such processes. So far, no signal has been confirmed as dark matter. Particle accelerators offer a third strategy. If WIMPs can be produced in high-energy collisions, then experiments such as those at the Large Hadron Collider could detect missing energy events consistent with dark matter particles escaping the detector. No confirmed WIMP production has been observed so far. The shrinking parameter space does not eliminate the WIMP idea, but it changes expectations. The simplest models are under increasing pressure. More complex scenarios remain possible. For example, WIMPs might interact primarily with leptons rather than quarks, altering detection signatures. They might belong to a hidden sector with its own forces, connected only weakly to the standard model. Despite the lack of detection, the WIMP framework remains important because it connects cosmology, astrophysics, and particle physics in a single quantitative model. The relic abundance calculation ties early universe thermodynamics to present-day measurements of dark matter density. The interaction scale links to known forces. Direct detection experiments translate cosmic questions into measurable laboratory signals. As detectors approach what is known as the neutrino floor, a new challenge emerges. At extremely low cross-sections, neutrinos become an irreducible background. Solar neutrinos can scatter off nuclei and mimic WIMP signals. Once detectors reach this sensitivity, distinguishing WIMPs from neutrinos becomes extremely difficult without new techniques. The absence of confirmed detection so far does not mean WIMPs do not exist. It means that if they exist, their properties are more constrained than before. The allowed mass range narrows. The allowed interaction strengths decrease. The models must fit both cosmological data and laboratory limits. The original appeal of the WIMP miracle lay in its simplicity. A particle with weak-scale interactions naturally gives the correct relic density after freeze-out. The required annihilation cross-section is on the order of 3 × 10 to the -26 cubic centimeters per second. That value emerges from balancing expansion rate and annihilation rate in the early universe. It is not inserted to match observations. It comes from thermal physics. Even with tightening constraints, many physicists continue to refine WIMP searches. Larger detectors are planned. Improved background suppression techniques are under development. The search extends across different target materials and detection strategies to avoid blind spots. The question remains open. WIMPs provide a clear, testable framework. They explain how dark matter could arise naturally from early universe physics. They connect cosmic abundance with particle interactions at the weak scale. Yet, after years of increasingly sensitive experiments, no confirmed signal has emerged. The allowed parameter space shrinks steadily. Regions once considered promising are now excluded. Remaining regions require weaker couplings, heavier masses, or more complex interactions. The search continues, driven not by assumption, but by measurement, with each experiment narrowing the possibilities and defining more precisely what dark matter could be if it belongs to the class of weakly interacting massive particles. Axion-photon conversion in magnetic fields. Not every dark matter candidate begins with astronomy. Some begin inside the equations of particle physics. Axions were not invented to explain galaxy rotation curves or gravitational lensing. They were proposed to solve a different problem entirely, one that appears in the theory describing the strong nuclear force. The strong force binds quarks together inside protons and neutrons. It is described by a theory called quantum chromodynamics, or QCD. QCD is extremely successful. It explains how quarks combine into hadrons and how those particles interact at high energies. But within the mathematical structure of QCD, there is a term that should, in principle, violate a symmetry known as CP symmetry. CP symmetry combines charge conjugation, which swaps particles with antiparticles, and parity, which flips spatial coordinates like a mirror reflection. In many processes in nature, CP symmetry is slightly violated. The weak force violates CP symmetry in certain decays. However, the strong force appears to conserve CP symmetry almost perfectly. The equations of QCD allow for a parameter, often called theta, that controls the amount of CP violation in the strong interaction. If theta were of order 1, the strong force would produce measurable electric dipole moments in particles such as the neutron. Experiments have searched for a neutron electric dipole moment with extreme precision. The result is that it is either zero or incredibly small. This creates a puzzle known as the strong CP problem. The theory allows CP violation in the strong force, but experiments show no sign of it. The value of theta must be extraordinarily small, less than about 1 part in 10 billion. There is no obvious reason within QCD alone for it to be so tiny. It appears fine-tuned. In the late 1970s, Roberto Pache and Helen Quinn proposed a mechanism to solve this problem. They introduced a new global symmetry that would dynamically drive the effective theta parameter towards zero. This symmetry is now known as the Pache-Quinn symmetry. When this symmetry breaks spontaneously, it gives rise to a new particle. That particle is called the axion. The axion is not inserted arbitrarily. It emerges as a consequence of making the strong force naturally conserve CP symmetry. In this framework, the troublesome theta parameter becomes a dynamical field. Instead of being fixed, it relaxes towards zero through the behavior of the axion field. The result is that CP violation in the strong force becomes suppressed automatically. The properties of the axion depend on the energy scale at which the Pache-Quinn symmetry breaks. In early versions of the model, that scale was near the electroweak scale, which would have made axions relatively heavy and easier to detect. Experiments quickly ruled out those visible axions. Later, models shifted the symmetry breaking scale much higher. That change made axions extremely light and extremely weakly interacting. Modern axion models predict particles with masses that can be far below that of the electron, often in the microelectron volt range, or even lower. For comparison, the electron has a mass of about 500,000 electron volts. An axion could be more than 1 trillion times lighter. Despite their tiny mass, axions could still account for dark matter. Their production mechanism in the early universe differs from the thermal relic picture used for WIMPs. Axions are typically produced through a non-thermal process known as the misalignment mechanism. In this scenario, when the Pache-Quinn symmetry breaks in the early universe, the axion field takes on some initial value that is not at the minimum of its potential. As the universe expands and cools, the field begins to oscillate around its minimum. These coherent oscillations behave like a cold population of particles. The energy stored in the oscillations acts as dark matter. Because the axion field oscillates collectively rather than being created and destroyed in thermal equilibrium, its abundance does not depend on annihilation cross-sections in the same way as WIMPs. Instead, it depends on the symmetry breaking scale and the initial misalignment angle. Axions are extremely weakly interacting. They do not carry electric charge. They do not participate in the strong or weak nuclear forces in the way ordinary particles do. However, they can couple very weakly to photons. This coupling allows an axion to convert into a photon in the presence of a strong magnetic field. The interaction between axions and photons can be described through an effective term in the Lagrangian that links the axion field to the electromagnetic field. In simple terms, when an axion passes through a region with a strong magnetic field, there is a small probability that it will transform into a photon. The reverse process can also occur, where a photon converts into an axion. This axion-photon conversion is the basis for many detection strategies. One of the most sensitive experiments searching for axion dark matter is the ADMX, short for Axion Dark Matter Experiment. A DMX is designed to detect axions that make up the dark matter halo of our galaxy. If axions are the dominant dark matter component, they should be passing through Earth continuously. Because they are extremely light, their energy is determined mostly by their mass, with a small additional contribution from their kinetic energy in the galactic halo. In ADMX, a strong magnetic field fills a microwave cavity. The idea is that an axion entering the cavity can convert into a photon in the presence of the magnetic field. The photon produced has a frequency corresponding to the axion's mass. Since axion mass is unknown, the experiment must scan across different frequencies. The microwave cavity acts like a resonator. When its resonant frequency matches the frequency corresponding to the axion mass, the conversion signal is enhanced. The expected signal is extremely weak, so the apparatus must be cooled to very low temperatures to reduce thermal noise. Sensitive amplifiers measure tiny excess power at specific frequencies. The scanning process is slow and methodical. The experiment tunes the cavity slightly, listens for a signal, then tunes again. Each frequency range corresponds to a specific possible axion mass. If axions exist within that mass window and have the predicted coupling strength, a narrow spike in power would appear at the resonant frequency. So far, ADMX has not reported a confirmed detection of axions. However, it has excluded certain ranges of axion mass and coupling strength. As the experiment improves, it extends its sensitivity deeper into theoretically favoured regions. Axion searches are not limited to ADMX. Other experiments use similar principles with variations in design. Some use different cavity geometries. Others explore higher frequency ranges corresponding to lighter axions. There are also experiments that attempt to detect axions produced in the Sun, where strong electromagnetic fields could generate them through photon conversion processes. In astrophysical environments, axion-photon conversion can also occur in strong magnetic fields, such as those near neutron stars. Observations of stellar evolution place constraints on axion properties. If axions couple too strongly to photons or electrons, they would carry away energy from stars too efficiently, altering stellar lifetimes. Observations of stars therefore limit the allowed coupling strength. The appeal of axions as dark matter candidates lies in several features. They arise naturally from a well-defined particle physics problem. They can be extremely light, which avoids some constraints faced by heavier candidates. Their production mechanism in the early universe can yield the correct dark matter abundance for reasonable parameter choices. Unlike WIMPs, axions do not rely on weak-scale interaction. Their mass and coupling strength are determined by the Pecay-Quinn symmetry breaking scale. This scale could be very high, which explains why axions are so difficult to detect. if axions form a cold, dark matter background, they would not behave like individual particles in the usual sense. Because their mass is so small, their number density would be enormous. The axion field would behave more like a classical oscillating field than a collection of discrete particles. This gives rise to the concept of wave-like dark matter behavior on very small scales. The search for axions is ongoing and expanding. New cavity designs, quantum sensors, and improved amplifiers aim to increase sensitivity. The parameter space defined by axion mass and axion-photon coupling is gradually being explored. Certain regions motivated by theoretical models have already been ruled out. Others remain open. Axions represent a different approach to dark matter compared to WIMPs. They are not heavy particles freezing out of thermal equilibrium. They are light fields emerging from a symmetry that solves a strong CP problem. Their existence would connect a subtle feature of quantum chromodynamics to the larger scale structure of the universe. The mechanism of axion-photon conversion in magnetic fields provides a clear experimental path. A dark matter axion entering a region with a strong magnetic field can convert into a photon with a frequency equal to its mass divided by Planck's constant. That photon can be detected as microwave radiation. The signal would be extremely narrow in frequency, reflecting the small velocity dispersion of dark matter in the galactic halo. Every improvement in magnetic field strength, cavity quality factor, and amplifier noise temperature increases the chance of detecting such a signal. The absence of a confirmed detection so far does not eliminate axions, but it restricts the combinations of mass and coupling strength that remain viable. If axions are found, they would simultaneously solve the strong CP problem and explain dark matter. If they are not found within the predicted ranges, the Pecci-Quinn solution to the strong CP problem may need revision, or dark matter may belong to an entirely different class of particles. Sterile neutrinos. Neutrinos already exist in the standard model of particle physics. They are light, electrically neutral particles that interact through the weak force and gravity. Three types are known: electron neutrinos, muon neutrinos, and tau neutrinos. These are called active neutrinos because they participate in weak interactions. They are produced in nuclear reactions inside stars, in radioactive decay, and in particle accelerators. Billions pass through your body every second without leaving a trace. Neutrinos have very small masses. For a long time, they were thought to be massless, but experiments on neutrino oscillations proved that they have non-zero mass. Neutrino oscillation means that one type of neutrino can transform into another as it travels. This behavior is only possible if neutrinos have mass and if the flavor states are mixtures of different mass states. The discovery of neutrino mass already tells us that the standard model is incomplete. The model originally assumed neutrinos were massless. Adding mass terms requires either introducing very small Yukawa couplings or extending the theory in some way. One natural extension introduces new neutrino states that do not interact through the weak force at all. These hypothetical particles are called sterile neutrinos. The word sterile refers to their lack of standard model interactions. Unlike active neutrinos, sterile neutrinos would not feel the weak force. They would not participate in beta decay. They would not scatter in detectors designed to capture neutrinos through weak interactions. Their only guaranteed interaction would be gravity. They could also mix slightly with active neutrinos, allowing indirect effects. Sterile neutrinos arise naturally in several theoretical frameworks. One important mechanism is the seesaw mechanism, which attempts to explain why active neutrino masses are so small. In this picture, heavy right-handed neutrinos are added to the theory. These right-handed states do not interact through the weak force. When mass terms are included that mix active and sterile states, the resulting mass eigenvalues split. One set becomes very light, corresponding to the observed neutrinos. The other set becomes very heavy. In some versions of the seesaw mechanism, sterile neutrinos are extremely heavy, far beyond the reach of experiments and irrelevant for dark matter. In other models, at least one sterile neutrino has a much lower mass in the kilo-electron-volt range. A particle in that mass range could serve as a dark matter candidate. Sterile neutrinos as dark matter differ from WIMPs and axions in several ways. They are fermions, like ordinary neutrinos. They are much lighter than typical WIMPs, but much heavier than axions. They interact only through mixing with active neutrinos and gravity. Because their mixing angle is small, their interactions are extremely rare. In the early universe, sterile neutrinos could be produced through oscillations from active neutrinos. Even though they do not interact directly, the mixing allows a small fraction of active neutrinos to convert into sterile states. The production rate depends on temperature, mixing angle, and the sterile neutrino mass. If the mass is in the kilo-electron-volt range, sterile neutrinos behave as warm, dark matter rather than cold dark matter. Warm, dark matter particles move faster than cold dark matter particles in the early universe. Their free-streaming motion can smooth out density fluctuations on small scales. This affects the formation of small galaxies and the structure of halos. Observations of the large-scale structure place constraints on how warm dark matter can be. If sterile neutrinos are too light, they would erase too much small-scale structure. The observed abundance of dwarf galaxies and the Lyman alpha forest in quasar spectra limit how light they can be. One of the most discussed observational hints related to sterile neutrinos is the so-called 3.5 kilo-electron-volt X-ray line. In 2014, two independent research groups reported an unexplained emission line at around 3.5 kilo-electron-volts in X-ray spectra from galaxy clusters and the Andromeda galaxy. The line did not match any known atomic transition expected from hot gas in those environments. The idea quickly emerged that this line might be due to the decay of sterile neutrino dark matter. A sterile neutrino with a mass of about 7 kilo-electron-volts could decay into an active neutrino and a photon. The photon would carry roughly half the mass energy, producing an X-ray line at around 3.5 kilo-electron-volts. Sterile neutrinos are not completely stable if they mix with active neutrinos. The mixing allows a slow decay channel. The lifetime can be much longer than the age of the universe if the mixing angle is small enough. In that case, most sterile neutrinos would still be present today as dark matter, but a tiny fraction would decay and emit X-ray photons. The reported 3.5 kilo-electron-volt line generated intense interest. If real and if due to dark matter decay, it would be the first direct non-gravitational signature of dark matter. The signal appeared in stacked spectra of galaxy clusters and in observations of the Andromeda galaxy. The strength of the line was consistent with expectations from sterile neutrino decay under certain parameter choices. However, the situation quickly became complex. Other observations did not consistently confirm the signal. Some instruments detected hints of a line, others did not see it at all. There were debates about background modelling, atomic emission lines from potassium or other elements, and instrumental systematics. One challenge in interpreting the 3.5 kilo-electron-volt line is that galaxy clusters contain extremely hot gas emitting many X-ray lines. Small uncertainties in atomic data or modelling of plasma conditions can produce residual features. Distinguishing a dark matter decay line from conventional astrophysical emission requires careful analysis. Subsequent studies using different telescopes produced mixed results. Some analyses supported the presence of an unexplained line near 3.5 kilo-electron volts. Others found no statistically significant excess when using alternative modelling methods or different datasets. The debate continues with no universal agreement. New X-ray missions with improved spectral resolution aim to clarify the situation. High-resolution spectroscopy can separate narrow lines more cleanly and identify whether the feature matches known atomic transitions. If the line is confirmed and its spatial distribution matches dark matter density profiles rather than hot gas distributions, that would strongly support a decay origin. If sterile neutrinos are the dark matter and have a mass around 7 kilo-electron volts, their decay rate must be extremely small to remain consistent with observed dark matter density today. The mixing angle required to produce the correct relic, abundance and decay rate lies within a narrow region of parameter space. Observations of the cosmic X-ray background also constrain how much decay radiation can be present. Beyond the 3.5 kilo-electron volt line, sterile neutrinos influence structure formation. Because they are warm dark matter candidates, they suppress small-scale structure below a certain length scale. This can potentially address some small-scale tensions in cold dark matter models, such as the number of predicted satellite galaxies around large galaxies. However, if the mass is too low, the suppression becomes too strong and conflicts with observations of early galaxy formation. Sterile neutrinos also affect the formation of the first stars and black holes. Their free-streaming length determines the smallest halos that can form. If small halos are suppressed, the timing and abundance of early star formation change. Observations of high redshift galaxies and the Lyman alpha forest provide constraints on these effects. Laboratory experiments also search for sterile neutrinos, though typically at different mass scales. Short baseline neutrino experiments look for anomalies in neutrino oscillation patterns that could indicate additional neutrino states. Some anomalies have been reported over the years, but none have led to a confirmed discovery of sterile neutrinos. These oscillation searches usually target electron-volt scale sterile neutrinos, which are too light to account for dark matter. The dark matter candidate version lies at much higher mass in the kilo-electron-volt range. The sterile neutrino hypothesis links cosmology, particle physics, and astrophysics. It extends the neutrino sector in a minimal way, adding right-handed states that are otherwise absent from the standard model. It provides a possible explanation for neutrino mass and a dark matter candidate in a single framework. The current status remains uncertain. The 3.5 kilo-electron volt X-ray line remains under debate. Some datasets show hints consistent with sterile neutrino decay. Others do not. Constraints from structure formation and X-ray observations narrow the allowed parameter space. No definitive detection has been made. If sterile neutrinos are the dark matter, they would form a diffuse halo around galaxies, similar to other dark matter candidates. Their gravitational behavior would be nearly identical on large scales. The differences would appear mainly on small scales due to their warm nature, and in the possibility of rare radiative decays producing X-ray photons. Primordial black holes. Not every dark matter candidate is a new particle. Some proposals suggest that dark matter could be made of objects that already fit within known physics. Black holes require no extension of the standard model. They form when enough mass is compressed into a small region so that gravity overwhelms all other forces. Usually, black holes form from the collapse of massive stars. But there is another possibility. Some black holes may have formed long before stars even existed. These hypothetical objects are called primordial black holes. The word primordial refers to their origin in the early universe, not in stellar collapse. In the first fractions of a second after the Big Bang, the universe was extremely dense and rapidly expanding. Small quantum fluctuations in density were stretched to cosmic scales during inflation. Most of these fluctuations were tiny, on the order of 1 part in 100,000, as seen in the cosmic microwave background. But if, on some scales, density spikes were much larger, gravity could have caused certain regions to collapse directly into black holes. The physics is straightforward in principle. If a region of space contains enough mass within its horizon size, and if pressure forces cannot counteract gravity, that region can collapse into a black hole. In the early universe, the horizon size was extremely small. That means primordial black holes could have formed with a wide range of masses, from tiny fractions of a gram to thousands or even millions of times the mass of the Sun, depending on when they formed. The mass of a primordial black hole roughly corresponds to the mass contained within the cosmic horizon at the time of its formation. Earlier times correspond to smaller horizon masses. Later times correspond to larger horizon masses. This creates a spectrum of possible black hole masses tied directly to conditions in the early universe. Primordial black holes do not require new particles. They are made from whatever matter and energy existed at the time of formation. Once formed, they behave like any other black hole of the same mass. They interact through gravity. They do not emit light except for extremely faint Hawking radiation in the case of very small masses. If enough of them formed and survived to the present day, they could account for some or all of the dark matter. The idea has existed for decades, but it gained renewed attention after the first direct detection of gravitational waves in 2015 by the LIGO. LIGO detected gravitational waves from merging black holes with masses around 30 times that of the Sun. These masses were somewhat larger than many astrophysicists expected for stellar origin black holes. That raised the possibility that some of these objects could be primordial. If primordial black holes exist in the right mass range and in sufficient numbers, they could merge and produce gravitational waves detectable today. The merger rate observed by LIGO places constraints on how many such black holes can exist. If they were too abundant, the merger rate would be much higher than observed. If they were too rare, they could not account for all dark matter. Gravitational wave detections from LIGO and other observatories continue to refine these limits. The distribution of black hole masses and spins observed in mergers provides clues about their origin. Stellar black holes inherit properties from their progenitor stars. Primordial black holes would not necessarily follow the same patterns. So far, the data do not require a primordial origin, but they do not completely rule it out for certain mass ranges. Another powerful constraint comes from gravitational microlensing. When a massive compact object passes in front of a distant star, its gravity bends the light from that star and causes a temporary brightening. The duration and frequency of such events depend on the mass and abundance of the compact objects. Surveys monitoring millions of stars in the Milky Way and nearby galaxies have searched for microlensing signals that would indicate dark matter in the form of compact objects. If primordial black holes with masses similar to stars made up most of the dark matter halo of our galaxy, microlensing events would be common. Observations have not found enough events to support that scenario. This rules out a large fraction of parameter space for primordial black holes in certain mass ranges, especially from around 1,000th of a solar mass up to several solar masses. The cosmic microwave background also provides strong constraints. Primordial black holes can affect the CMB in several ways. If they accrete gas in the early universe, the infalling matter heats up and emits radiation. That radiation can ionize hydrogen and alter the recombination history. Changes in the ionization history leave imprints on the temperature and polarization patterns of the CMB. Observations of the CMB are extremely precise, and any significant energy injection from accreting primordial black holes would likely have been detected. CMB measurements limit the abundance of primordial black holes in certain mass ranges, particularly those heavy enough to accrete efficiently at early times. If too many existed, the ionization history would deviate from what is observed. The agreement between theoretical models and CMB data therefore restricts how much of the dark matter could consist of primordial black holes in those ranges. There are also constraints from dynamical effects. Massive compact objects passing through stellar systems can disrupt star clusters or heat galactic disks. Observations of the stability of wide binary star systems provide additional limits. If dark matter were composed mostly of heavy primordial black holes, these systems would show signs of disruption that are not observed. Very small primordial black holes face another issue. Black holes emit Hawking radiation. The smaller the mass, the stronger the radiation. Extremely small primordial black holes would have evaporated completely over the age of the universe. The absence of intense gamma-ray backgrounds from such evaporation constrains the abundance of primordial black holes below a certain mass threshold. Taken together, these constraints carve out allowed and excluded regions across a wide range of masses. Some windows remain open, especially in certain intermediate mass ranges and in very small mass ranges where constraints are weaker. However, no mass range currently allows primordial black holes to easily account for all dark matter without tension with at least one set of observations. The interest sparked by LIGO detections brought attention back to these windows. If some fraction of merging black holes observed by LIGO were primordial, that could provide indirect evidence. But alternative explanations based on stellar evolution remain consistent with the data. The merger rate, mass distribution, and spin measurements so far do not require a primordial component. Primordial black holes have one conceptual advantage. They require no new fundamental particles. They rely only on known gravitational physics and possible enhanced density fluctuations in the early universe. However, generating sufficiently large density spikes without conflicting with the smoothness observed in the CMB is challenging. Models that produce such spikes must be carefully constructed to avoid overproducing black holes or disrupting known cosmological features. How we're searching for it. Dark matter does not emit light. It does not absorb light. It does not reflect light. Every image of a galaxy shows only the small fraction made of normal matter. The rest is inferred from gravity. That makes the search for dark matter different from the discovery of most particles in physics. It cannot be seen directly through telescopes. It has to be detected through its rare interactions or its gravitational effects. The search happens along three main paths. Direct detection experiments attempt to measure dark matter particles passing through Earth. Indirect detection searches for the products of dark matter annihilation or decay in space. Particle colliders try to create dark matter in high-energy collisions and identify it through missing energy. At the same time, cosmological simulations and galaxy observations test whether the dominant theoretical model, cold dark matter, fully matches reality on small scales. If dark matter consists of particles that fill the Milky Way halo, then Earth is constantly moving through that halo. The Sun orbits the centre of the galaxy at about 220 kilometres per second. Dark matter particles, whatever they are, move with characteristic speeds of a few hundred kilometres per second relative to the galaxy. That means a steady wind of dark matter passes through the solar system. Direct detection experiments are built on a simple idea. If a dark matter particle interacts even extremely weakly with ordinary matter, then occasionally it may collide with an atomic nucleus. That collision would transfer a tiny amount of energy to the nucleus, causing it to recoil. The recoil energy is small, often just a few kilo-electron volts, but sensitive detectors can measure it. The difficulty is background noise. Cosmic rays constantly bombard Earth's surface. Natural radioactivity exists in rocks, air, and even detector materials themselves. These background events can produce signals much more frequently than the rare interactions expected from dark matter. To reduce this interference, direct detection experiments are placed deep underground. Underground laboratories are located in mines or beneath mountains. Layers of rock shield the detectors from cosmic rays. Additional shielding materials surround the detectors to block radiation from the surrounding environment. The goal is to create an environment as quiet as possible, where only extremely rare interactions remain. Many direct detection experiments use noble liquids such as xenon or argon. These materials are dense and scalable to large masses. When a nucleus recoils in liquid xenon, it produces a small flash of light and frees electrons. Sensors detect the light and measure the charge. The ratio of light to charge helps distinguish nuclear recoils from background events caused by electrons. Other experiments use cryogenic crystals cooled to extremely low temperatures. In these detectors, a nuclear recoil produces tiny vibrations in the crystal lattice, called phonons. Sensitive thermometers measure the resulting temperature rise, which is often a fraction of a degree above absolute zero. The expected signal from a dark matter particle is very rare. A detector containing tons of material might see only a few events per year, depending on the interaction cross-section. That is why experiments aim to increase detector mass while reducing background levels. The key observable is the recoil energy spectrum. The shape of this spectrum depends on the mass of the dark matter particle and its velocity distribution. If a signal appears above background expectations and follows the predicted shape, it could indicate dark matter. So far, no confirmed dark matter signal has emerged from direct detection experiments. Each new generation improves sensitivity and rules out more parameter space for certain types of particles, especially WIMPs. The upper limits on the interaction cross-section have dropped dramatically over the past 2 decades. A major challenge is the neutrino background. Neutrinos from the Sun and from cosmic ray interactions in the atmosphere can scatter off nuclei and produce signals similar to those expected from dark matter. At extremely low cross-sections, this neutrino background becomes unavoidable. This region is sometimes called the neutrino floor. Below this floor, distinguishing dark matter from neutrinos becomes statistically difficult. Despite the lack of detection, direct detection remains one of the most powerful methods. It directly tests whether dark matter particles interact with normal matter at measurable rates. Every improvement either brings the field closer to discovery or eliminates entire classes of models. If dark matter particles can annihilate with one another, they may produce ordinary particles such as gamma rays, electrons, or neutrinos. These annihilation products could be detectable from regions where dark matter density is high. The galactic center is one such region. Dwarf spheroidal galaxies orbiting the Milky Way are another. These galaxies contain high dark matter densities and relatively little background emission. Indirect detection focuses on observing excess radiation that cannot be explained by known astrophysical processes. Gamma rays are especially important because they travel in straight lines and point back to their source. If dark matter annihilation produces gamma rays, telescopes could detect them as an excess over expected backgrounds. The Fermi Gamma Ray Space Telescope has been one of the most important instruments in this search. It surveys the sky in high-energy gamma rays and has collected data for many years. One intriguing feature observed in Fermi data is the so-called galactic center excess. The galactic center excess refers to a surplus of gamma rays detected near the center of the Milky Way, with energies in the range of a few giga-electron volts. The signal appears roughly spherical and extends several degrees from the center. Its spectrum and spatial distribution initially seemed consistent with expectations from WIMP annihilation, with masses around tens of GeV. However, the galactic center is a complicated environment. It contains many sources of gamma rays, including pulsars, supernova remnants, and cosmic ray interactions with gas. Further analysis suggested that a population of unresolved millisecond pulsars could explain much of the excess. The debate continues, with studies supporting both interpretations. Indirect detection also includes searches for signals from dwarf spheroidal galaxies. These small galaxies have high mass-to-light ratios, meaning they contain large amounts of dark matter relative to stars. Observations of dwarf galaxies with gamma-ray telescopes have not detected significant excesses. These non-detections place strong limits on the annihilation cross-section of WIMP-like particles. If dark matter particles decay rather than annihilate, they could produce characteristic spectral lines. X-ray observations have been used to search for such lines, particularly in the context of sterile neutrino models. So far, no universally accepted decay signal has been confirmed. Cosmic ray detectors also contribute to indirect detection. Excesses in positron or antiproton fluxes could hint at dark matter annihilation. However, astrophysical sources such as pulsars can also produce these particles, making interpretation difficult. Indirect detection depends heavily on modelling astrophysical backgrounds. Unlike direct detection, where backgrounds can be measured and controlled in the laboratory, astrophysical environments are complex and sometimes poorly understood. That makes it harder to claim a definitive detection. Still, indirect detection probes different properties than direct detection. It tests whether dark matter particles can annihilate or decay into detectable radiation. Combined with other methods, it narrows down the range of viable models. Another approach is to create dark matter particles in controlled experiments. High-energy particle colliders accelerate particles to near light speed and smash them together. If enough energy is concentrated in a collision, new particles can be produced according to Einstein's equation E equals mc squared. The CERN operates the Large Hadron Collider, the most powerful collider in the world. It collides protons at energies of several tera-electron volts. If dark matter particles couple to standard model particles at energies accessible at the LHC, they could be produced in these collisions. Dark matter particles would not be detected directly in collider detectors because they would pass through without interacting. Instead, their presence would be inferred from missing energy. In a proton collision, energy and momentum are conserved. Detectors measure the energy and momentum of all visible particles. If a collision produces invisible particles, there will be an imbalance in the measured momentum, especially in the plane perpendicular to the beam. These events are called missing transverse energy signatures. Physicists look for events where visible particles recoil against something invisible. For example, a quark might emit a gluon or photon, and the rest of the energy goes into producing dark matter particles that escape detection. The visible particle provides a trigger, while the missing energy indicates something unseen. Searchers at the LHC have looked for many possible signatures consistent with WIMPs and other dark matter candidates. So far, no confirmed evidence of dark matter production has been found. The data have placed strong limits on models where dark matter interacts with quarks or gluons through certain mediator particles. There are several reasons why the LHC may not have found WIMPs. One possibility is that dark matter particles are heavier than the energies accessible at the collider. Another is that their interactions with standard model particles are weaker than expected. It is also possible that dark matter belongs to a hidden sector with very limited coupling to ordinary matter, making production extremely rare. Collider searches complement direct and indirect detection. They probe interactions at high energies and can test models that might be difficult to detect through astrophysical means. Even null results are valuable because they constrain theoretical possibilities. While experiments search for particles, cosmologists test the cold, dark matter model against observations of galaxies. On large scales, the CDM model matches observations extremely well. It explains the cosmic microwave background, large-scale structure, and galaxy clustering. On smaller scales, however, some tensions have appeared. One issue is the core cusp problem. Simulations of cold dark matter halos predict that density should increase sharply toward the centre, forming a cusp. Observations of some dwarf galaxies suggest flatter central density profiles, called cores. The difference between a steep cusp and a shallow core has been debated for years. Another issue is the missing satellites problem. Simulations predict that a Milky Way-sized halo should contain hundreds of smaller subhalos. Observations initially found far fewer dwarf satellite galaxies than predicted. However, improved surveys have discovered more faint dwarf galaxies, reducing but not eliminating the discrepancy. The too big to fail problem refers to the prediction that the most massive subhalos in simulations should host visible dwarf galaxies. Some of these predicted halos appear too dense compared to observed satellites. They seem too massive to have failed to form stars, yet corresponding luminous objects are not seen. These small-scale problems raise questions about whether cold dark matter is complete. One possibility is that dark matter has additional properties, such as self-interactions, that modify halo structure. Another possibility involves baryonic feedback processes. Baryonic feedback refers to the effects of ordinary matter, especially gas and stars, on dark matter distribution. Supernova explosions release enormous energy into surrounding gas. That energy can cause rapid changes in gravitational potential. Repeated bursts of star formation and supernova activity can redistribute matter and flatten central density cusps into cores. Hydrodynamic simulations that include baryonic physics show that feedback can significantly alter halo structure, especially in dwarf galaxies. These simulations reduce some of the tension seen in earlier dark matter-only simulations. Similarly, the missing satellites problem is partly alleviated when considering that not all subhalos necessarily form stars. Processes such as reionization can prevent gas from cooling in small halos, suppressing star formation. This means many predicted subhalos could remain dark and undetectable. The too big to fail problem also becomes less severe when baryonic effects are included. Gas outflows and tidal interactions can reduce the central densities of subhalos, bringing simulations closer to observations. Small-scale challenges remain an active area of research. They test whether cold dark matter with simple, collisionless behaviour is sufficient, or whether additional physics is needed. So far, no alternative model has matched the large-scale success of CDM, while clearly outperforming it on small scales. The universe we see is only a fraction of what exists, and simulations like the Millennium Simulation help us understand how it formed, by tracking billions of dark matter particles with N-body techniques, showing how they collapse into halos where gas collects and stars form, creating galaxies and weaving a vast cosmic web of filaments connecting clusters across space. Detecting dark matter would confirm new physics beyond the standard model, validate early universe predictions, reshape particle physics, and could even lead to unforeseen technological advances.